I actually made a change in my presentation last night. So I've been watching the audience over here over the past weekend here. Decided there was enough of you that had not seen this material that I presented at the APS March meeting. That I thought the message is important enough and simple enough that it's worthwhile giving here. I'll save my material my new material for the next round. So, giving you a rather provocative title here, I'm implying there's some sort of fight. It's DWave versus DWave. Who's going to win? I like those sorts of fight because I always win then. All right, so of course, we're using a DWave processor. That's the extent of my lecture on the DWave processor. I love it that I don't have to give these lectures about hardware bits any longer. I leave that for other people now. So, of course, we had our fun with these processors within the past year. If you've been following the story at all, you know about these two publications. What we did in both these cases, we took a DWave processor and we turned it into a simulator of a condensed matter system. And we were studying phase transitions in the quantum regime. So we were actually turning the transverse field and the transverse field Ising model and looking at phase transitions that are happening along the way. Now, neat as those presentations, as those experiments are, there is just one message I want you to take away from them that's important, that I feel is really important and sometimes understated, which is why are we building quantum computers in the first place? And the idea is to simulate complex systems, things that we cannot, or hopefully down the road, we cannot access with classical computation resources. In some ways, I consider these two experiments to be the first real tentative steps into that space, where we actually take an early generation quantum processor, use it to simulate a completely different system, so not the native system at all, and we actually pull out physics of that related to that simulated system. And we did it on an appreciable scale at this point, so I would say this is certainly a first in the field of quantum computing. So it's very different than thinking about, say, running native chimera problems, or you look at the various quantum supremacy efforts that are underway right now. In all those situations, you're running something that's native to the architecture that you've built, and you're trying to get to the point of saying, well, if I hypothetically just sort of turn a blind eye to the fact that this thing is just simulating itself in a lot of ways, this would be a hard problem. This takes it to the next level. We said, all right, forget that. We're no longer just simulating a D-Wave chimera. Let's actually look at things like the cubic lattice on the left, or this other variant of a triangular lattice on your right here, and pulling out the physics of phase transitions. So, enough of that. There's this question, though, but where is that quantum advantage? So this is something that's on my mind every day when I go to work at D-Wave. We built these things ostensibly to be solving hard problems and getting to solutions faster. And it certainly bothers me that there's no sort of real strong signal that says, yes, indeed, this is the case. You have a viable technology here that's going to go that distance. And the other thing that sort of really bothers me in the end is this question here, but what does noise or coherence have to do with it? I'm an experimental physicist, and like everyone else in the gate model community who's building these systems, I am obsessed with noise. You ask any of my coworkers at D-Wave, and it's sort of one of my favorite topics. I tend to bludgeon people at the meetings whenever the meeting may be about various processors or servers and stuff like this. I'm always like, well, when are we going to deal about noise? It's just what I do in D-Wave. It's my job. So I want to actually address this latter question here. And we're going to do this in a very experimental way. So on that theme of looking for a fight that I give you with the title, all good fights will start with someone looking for a problem. So indeed, we're going to do that. We need to look for a particular problem throughout the processor, through which we can glean some information. Because, of course, that's the way you interrogate a D-Wave processor. You ultimately pose a problem, you get back a classical answer, and it's what you do with that classical answer thereafter that gives you information. So if you really want to see the impact of noise on the D-Wave processor, you need to be careful about how you choose your problems. First point that I'll bring up here is you want to choose problems that have favorable phase transitions. If you want all the gory details, of course, you can go find Helmut. He wrote a wonderful article on this years ago now, looking at it from the classical perspective and saying, if you have a system where the phase transition from a paramagnetic or disordered phase into that final spin glass or ordered phase, if that classical phase transition is going to t equals 0, well, good luck getting down there with any sort of noisy system. Really put some Additional flavor on that is when you think about this in the quantum regime, so at a finite transverse magnetic field, I always go back to something called the Merman-Wagner theorem. Does everyone know what that is among the physics community? Yes, I knew Frank would, so of course. So just in a nutshell, that general theorem, what it describes or states very clearly is that for systems that are two-dimensional or less, if you have a continuous degree of freedom for your spin variables in that system, then you're going to have zero energy modes. We call them magnons. So if you have something like a pure ferromagnet in 2 dimensions, and you allow your spins on this lattice to smoothly and continuously vary between spin up and spin down, well, I can come up with an excitation in that system where it's spin up here, spin up, cant it off a little bit in the next nearest neighbor, cant the next one a little bit more, like this. And I can work myself around to eventually being into a spin down state. So if I had an overall ferromagnet that should be either aligned all spin up or all spin down, this is a very low energy way to put a kink in that or a distortion in that where I'm changing state. And that low energy mode, that wave, is called a magnon. So in a mean field sense, when you look at the transverse field Ising model, you're looking at finite tunneling energy, if you will, you can actually go from spin up to spin down just by by virtue of that tunneling energy. You can sort of envision that as a 2D spin vector and cant it over. So it tells you in low dimensional systems, you better watch out. There are going to be low energy excitations, which when you run quantum annealing means you're going to end up being projected into excited states. The other thing you got to watch for is, do you have a problem class where you can clearly see an optimal annealing time? And if you want the full answer on that, you go to this guy over here, Daniel. My sort of takeaway on that, and the way I see it, is what you want to do is you want to be able to pose a problem to the hardware where you can still catch it in the act of actually trying to find its way into the ground state. So you're actually probing the system on annealing timescales that are comparable to the dynamical timescales that matter, somewhere right around the phase transition, presumably. So, of course, when I look out a lot of work that's been done on the DWave processor, if you were to measure, say, ground state probability versus anneal time, there's an awful lot of cases I've seen out in the literature and done within DWave as well, where that thing is pretty much flat. And what it tells you is that all the action has happened long before that shortest anneal time that we currently allow external users to use, which is 1 microsecond. So within 1 microsecond, it's game over. The system has done its dynamics. There's nothing else to see. So if you're looking for scaling or anything like that, trying to pull out sort of the more fundamental physics of what's happening, you're too late at that point. You're already looking at steady state properties, if not thermal equilibrium. And of course, the third point is the unknown unknowns. So have we really thought of everything that impacts these problem classes? What about structure and the noise spectral density? Are there quirks to the hardware that we haven't really ferreted out at this point? So of those, I just bundle them all up in here and say, well, are there other things that we have not thought of that are going to affect ground state probabilities in some substantial way? Okay. So it ends up we are well on our way there to finding one problem class where you can at least satisfy 2 of these 3 constraints straight out of the gate. And that's this cubic lattice instances. So it's going back to that science manuscript that we published last summer. So in the lead up to actually producing that manuscript and looking at phase transitions, we of course had to look at the spin glass problems that we were generating. So just to give you a pictorial representation of what they look like, it's an 8 by 8 by 8 cubic lattice, nearest neighbor interactions, and you have the ability to tune the sign of the interactions between those nearest neighbors. So I'm just looking at some plus minus 1 problems on a 3D lattice. So as I've drawn here, hopefully you can make it out. As I say, the gold bars are -1. They're a ferromagnetic interaction, so spins want to be parallel aligned. And then the silver bars are the anti-ferromagnetic interactions. So here's a particular example. Red and blue balls there you can read off as spin up and spin down, say. And here's a particular ground state configuration for this guy. This is a nice problem class because what you can do is you can start from incredibly easy, which is start with, say, all anti-ferromagnetic interactions or all ferromagnetic. Either way works just fine. Well, that just gives you an ordered phase. So super simple problem. And then you can start doping in the ferromagnetic interactions to that otherwise anti-ferromagnetic lattice. And what you find is inevitably there's a critical doping out there somewhere where the problems go from incredibly easy to getting incredibly hard. There's a nice steep edge there in problem hardness. So what I've represented here, for example, is a spin glass, where it's a 50-50 mixture of these spin-up or ferromagnetic and anti-ferromagnetic interactions, and you really can't pick out any order by eye between the red and blue balls here. So nice problem class. We've got our favorable phase transitions. We're in a 3D system, so I don't have to worry about the whole Merman-Wagner theorem or any intuition behind that. Hard enough to make the processor sweat, and we knew that already, so we already found that we could find these optimal anneal times for the system. They were within the experimental constraints of what we could measure. But are these problems sensitive to noise? Well, that's the big question. So we could, of course, generate a whole bunch of theory about that and try to argue, well, this way and that way. I'm an experimentalist. I like to measure things. So here was the proposed experiment. Let's go ahead, make two nominally identical QPUs. We're going to use the same design, but we're going to fabricate them very different ways and see very different noise properties in those two processors. So what we want to do then is run the very same problems, one-to-one on each of these processors, and we want them to fight it out. We want to see which one wins. So there's our noisy brawl. We're going to have two processors, two different noise characteristics, and we're going to have them beat it out. So, of course, we had to build an apparatus to do that. So I really hope Chris Quintana is in the audience today, because I'm going to leak some very, very sensitive DWave IP. So we had to build a special apparatus to do this with two QPUs in it. And this is what it looks like. So, of course, here's our two processors. You can see there, I'll label them as QPU, as Fab1 QPU. The other one is Fab2 QPU. These are, in fact, the systems that you have available online right now. So the DWave 2000Q1 is the sort of standard-ish noise parameters that you had for existing DWave processors that are out in the wild right now. The DW2000Q-5, that's what we've colloquially been referring to as the quote-unquote lower noise processor. So manufactured one of our experimental fabrication variations. So one of the things we often don't talk about in the outside world is DWave, we have a fairly intensive material science program. And what we do is we're often running short loops where we're testing out variations in fabrication, testing out various materials and different processes. And when we feel like we've got a hit, when we feel like we've got something that's manufacturable and making an obvious difference in noise, then we go the full mile of making a whole new processor out of it. And we've really reached that point where the yields are good enough and the manufacturability is there with these processes that we're able to do this. And we're getting reasonably reliable at it. And of course, this is not the end of the road. We have other versions of this on the go. In fact, the next experiment on this line was just finishing up calibration as I left Vancouver last week. Okay, so what do I mean by a difference in noise between these processors? I'll try to sum it up in this one single graph here. What you see here are pairs of resonant tunneling peaks deep in the incoherent tunneling regime. So of course, brings the obvious question is, well, if I'm doing some sort of quantum computation, why am I looking at an incoherent tunneling measurement? Wouldn't I rather measure coherent properties? Ends up, this is a very easy measurement for us to do on full-scale processors where we don't have access to high bandwidth, fast lines. So if you're typically looking at gate model systems, often you have those controls where you're pumping the system between ground and first excited state, often with resonant excitation. D-Wave processors, we have very tight bandwidth limits on all our bias lines because we're trying to limit the amount of noise that's going down from the external environment at 300 Kelvin and reaching the mixing chamber. So we end up having to look at our systems where the dynamics are relatively slow. So this pushes us out into the incoherent tunneling regime. But nonetheless, it's a useful measure. That width of these spectral features, so you can see there's pairs of peaks, red and blue respectively. What these are tunneling processes where we initialize a single physical qubit in one of its wells of the double well potential, and we measure the rate at which it leaks across the other side. And we do it the opposite direction, hence the pairs of peaks. One's going from left to right, and one's going from right to left. With the blue peaks here, they're pretty much right on top of each other, but there are indeed two peaks in there. Ends up that width is related to T1 processes. So those relaxation or excitation processes are going to happen when you're exchanging energy with the environment. It's a measure of the integral of the noise spectral density at relatively high frequency. So you can actually go from here and back out T1s if you wish. You have to have a model for what that noise spectral density shape looks like, but you can then calibrate against it. What I want you to take away from this is comparing the widths of the Fab1 and Fab2. You can see there's about a factor of 5 difference between those two processors. So just keep that in mind. It's about a factor of 5 difference in what's looking like the decoherence processes, or those energy exchange processes. Okay. Now, we're not completely lawless here. We'll have to lay down some rules for our fight. How are we going to do this? So the first thing we're going to do is we're going to take a spin glass instance, randomly generate a spin glass instance on the DWave processor, and we're going to run it lots of times, say 100,000 times, as a function of the anneal time. So we'll get lots and lots of data. Next thing we're going to do is we're going to plot that up. Here's an example plot right here. It's ground state probability versus anneal time on a log scale here. The important factors to see here, you see this monotonically increasing function. I've just put a phenomenological function on the data here. This is something I've grabbed from the spin glass literature that I find just sort of does the job and helps me with my data analysis. I'm not reading anything in particular into the final fits of these parameters. The other thing you'll see on my plot here is that gray box on the bottom that I label as 10 to the 5 reads. There's my statistical noise floor for that measurement. So if you see something hitting that noise floor, like that one last datum at 1 microsecond anneal time, obviously I shouldn't read much into it. I put Poisson statistic error bars on that. It's either ground state or it's not. And you can see that that error bar obviously goes right down to 0. So discount that result. Just throw it out. You should concentrate on the things where are well resolved within the error bars. Okay, so we take that thing, we convert it to a solution time, as I call it. Just a very simple variant of what people have been calling time to solution. It's a much simpler formula that I present here. It just says take the anneal time, divide by the ground state probability. It's a very intuitive expression. For instance, if my probability of seeing the ground state is 1 in 1,000, then that means my solution time probably means I have to run the thing 1,000 times, multiplied by the anneal time. So very intuitive sort of expression, works just fine for what we're going to do here. Then we're going to repeat those steps, 1 through 3. We're going to do that for 100 randomly generated instances, identical instances run on each processor, and we're just going to ask that simple question, which one wins? Okay. So first thing is just a bit of shadow boxing, is a warm-up on one processor. And this is embedding details. This has been a source of confusion. I've had conversations about this with a few folks after the APS March meeting about this. I think there's a lot more to do in this area, but I'd like to go through this point here. So the important thing is we're looking at these cubic lattice problems. They are an embedded problem. They are not a native chimera problem. And this means you're using logical qubits or chains. An important point here is that chains are not equivalent to a single logical qubit, except in that asymptotic limit where the tunneling energies or the transverse field energy is going to 0. Then these bits are very much locked with certainty to each other. If you think about what's happening early in the quantum annealing process, if I have a chain of 4 physical qubits, if I apply a bias on one end of my chain, it sort of works its way down to the end, but not with full strength. Whereas if I push one of the qubits that are more towards the middle, well, it tends to push the 2 on the either ends much stronger. And ends up the same sort of thing happens when you couple chains together. So if you look at my forearms here, and we're going to call them 2 chains, if I have an interaction like this where I have 2 chains butting into each other, it looks different than this configuration where they're crossing to each other. So I actually get a stronger interaction in the crossing configuration than I do in this end-to-end configuration. So this ends up being something that's very predictable, and you can actually do something about it. So what I'm going to first do is, first data that I'm going to show you here, I'm going to show you example results for 3 spin glass problems first. I'm going to label one of them easy, one of them mean, and one of them hard. I'll show you by my final graph where I got these data from, where I got these 3 instances from. And it'll be clear at that point why they're easy, mean, and hard. So there's a plot of, you can see 2 traces in here. So the red, the blue, and the black, or the gray one, which I labeled hard. You can see there are no data on this graph. The processor did not solve it. So in particular, let's go through a little more detail here. So the easy instance, that was what I showed you as my example earlier. You can see we can pick out a minimum annealing time within a factor of 2. I'm fine with that. I'm not aiming for precision here. The mean, you can see it's actually into that light gray box labeled 10 to 5 reads. That's my Bermuda Triangle statistical noise. So what I had to do to actually see the the results from that mean instance was I had to crank up number of reads to 10 to the 6, which is that darker gray triangle you see up there. And then I could actually see those results from the mean instance and pull a minimum anneal time. Whereas that hard instance, I did up to 10 to the 6 reads for every anneal time. Nothing showed up. There were no solutions there. So, of course, as I just told you, is that coupling chains is not the same as coupling physical qubits. And what one can do is you can actually calculate the eigenspectra for coupled physical chains just based on the device parameters alone. And what you can do is calculate those eigenspectra as a function of the annealing parameter. You'll see that difference in energy, in coupling energy. And all you need to do is just rescale those coupling energies right around where you think the phase transition is going to happen for that system. And I found you can be pretty rough with that. You don't have to know that point in S, the anneal parameter, down to 6 digits precision to find out where the phase transition is going to happen. You get it within 1 digit of precision. It's basically you can do a correction that's good enough that's going to impact solution quality. So if I go ahead and do those corrections as I've laid out in the supplementary information for that science manuscript, then you get these bolder data that I presented here. Again, color coordinated with what you see there for easy, mean, and hard. So in all 3 cases, you can see things got better. Not so much for the easy instance, didn't seem to do much for me, but clearly once I get to the mean instance, it's dropped things down quite considerably. And lo and behold, certainly within 100,000 reads, I've been able to see that hard instance now. So we now actually can pull out solution times for all three cases. Now, if I look at the relative advantage, just by changing my embedding alone, you can see it's a factor 3 for the easy one. I get a factor 100 improvement for the mean. And I get a bounded factor of 500 improvement on that hard one. Again, I say it's a bound because I don't have any concrete results for the non-corrected hard instance. Okay, so the point I want you to take away here is, at least for the hard instance, correcting your embedding just upon very, very rough knowledge of where the phase transition is happening is good enough to give you a 500x increase in performance on these particular problems. Okay, so on to the main event. Let's have these two processors fight it out. Which one's going to win? So the first graph I'm going to show you, this is a repeat of those corrected embeddings or conditioned embeddings on the QP1 processor. So the standard DW2000Q type system. Okay. There's the new processor, the lower noise processor, so the Fab2 processor. Here, it's a little more obvious that you can see there obviously has been a big change on the easy instance alone. It looks like there's just this prefactor scaled things down. But when you look at the mean and hard instance, you can see, yes, it looks like we're getting solutions faster, but you also see something else that's happening. Look at where that minimum anneal time is. You can see that shifted back for the lower noise processor. It really tells you the dynamics are faster in these systems. So that's an important point related back to Daniel's last lecture here, is if you want to ask, well, is this improvement, did it really come from an improvement in precision, maybe, from just dealing with the noise, or is it something dynamical? I would argue that this is something dynamical. We have a processor where the spins are actually trying different spin configurations faster. Okay. As for the relative speed ups and all these things, you can see the 20x improvement for the easy instance, and then 30, 40, and 40 times for the mean and the hard. So, final question here, of course, is did I just cherry pick some particular instances to illustrate something, or is this representative of the overall behavior? So here are the results for those all 100 instances that I ran on the processor. We'll plot this as a correlation plot. So the Fab1 results, so our standard DW2000Q horizontal axis, lower noise processor on the vertical axis. And what you see here is there are indeed some scatter here, but you can more or less draw straight lines on this log-long plot, which just tells you there's an overall scale factor in performance between these two processors. And it ends up on the average case as a 25x improvement in favor of the Fab2 process. So again, to repeat the important message here is we made about nominal factor 5 improvement in the decoherence properties, and it gives you about 25x improvement over here in performance. So enough where we can see a modest change in noise is actually given a more substantial change in how the system behaves. Okay, so tidy up here. What do I want you to take away from this? So the first thing, this is one of my more important messages, and something that I'm actively working on right now in the context of applications, is The lessons that we learn from studying condensed matter systems, so working with a cubic lattice, measuring phase transitions, yes, there's all good stuff there, and it certainly points to an interesting direction, and perhaps the most viable direction for actually using quantum computers for their intended purpose. They nonetheless have relevance back here and towards the more application space if you're trying to use the D-Wave processor as a problem solver. So as I said, it really, in a lot of ways, I feel like the interesting problems in D-Wave processors are inevitably embedded problems. And so I feel like a lot of the things that I've described in terms of how you actually adjust your Hamiltonian that you pose to the processor based upon rough knowledge of the phase transitions, I think that's going to have a lot of relevance in the application space. So as I said, I'm actively working on that right now. I've been working on that project for about 5 weeks. Hopefully by the end of the summer, I'll have a little more to say about that. The other thing I want you to carry away is that modest reductions in the noise give a larger increase in performance here. We don't know, I can't explicitly state what is the mechanism here. There is certainly some speculation out there in the literature about where it may very well be coming from, but it all is a good thing. Quite frankly, if we reduce the noise and I saw performance get worse, I'd be pretty disappointed. I'd probably take up a career in knitting or something like that thereafter. But most important, this is the message that I really want you to take away from this, is there's a lot more that we can do. We can certainly have barely begun on this road of actually increasing or improving the coherence, reducing noise within the context of a scalable processor. D-Wave's whole approach into this quantum annealing picture has been a little bit backwards compared to what a lot of folks have considered. Often folks want to focus on one device or few devices, try to make them perfect, and then scale up. And what you find is you can paint yourself into a corner quite often doing that. Now, arguably, maybe we've painted ourselves into a different corner here. We've just decided we're going to try to build the scalable thing first, use that as constraints, and then do the material science that we need to do to reduce that noise. So I feel like there's a long ways to go. Everything that you've looked at to date in terms of scaling of D-Wave processors, I would say, watch out, things are going to change. We have additional experiments underway, and I hope to be able to show you them soon. All right, and with that, I'm done.
So, time for questions. So here in the front.
Hi, on your slide 12, where you're showing the MRT peaks, was there any difference in persistent currents between Fab 1 qubits and Fab 2 qubits?
Nope, they were quite close. So there's a difference in persistent current in those measurements, yes, because we had to bring the tunneling rates into line with each other. So we're aiming for the same maximum tunneling rate. So obviously with the lower noise processor, we had to go out deeper, or at lower tunneling energy, which means higher persistent current. But just to clarify, the parameters between these two processors, they were within, I believe, 95% of each other, roughly. So the energy scale. So they were quite comparable.
So don't get me wrong, I don't want to put too much emphasis on measurements of coherence, but it is a useful metric for the fab and all the design issues. And I just wonder if you can at least guesstimate, given models and given the measurements that you've seen.
Yeah, if you want a number you can take home in your luggage, let's say 20 nanoseconds, somewhere around there.
Yeah.
T1, yes.
There's a question here in the front.
Thank you. Is it possible to go back to the slide where you had the good embeddings and the bad embeddings? There was the figure with 10 to the 5 scaling and 10 to the 6 scaling.
10 to the 6?
I think it was 10 to the 6. Let's see how my memory works.
Wasn't that dramatic? I wish. Let's see. Just the embedding alone. That one.
A little bit earlier than this, where it's the same figure but with a little bit less of the.
Yep.
Okay, yeah. So what I see there is the blue and the red is 10 to the 5 and the blue is 10 to the 6 in the legend.
That's not speed up. That's number of reads.
The number of reads.
Yes,
Okay.
number of reads. That way
Very
you
big
have a
difference.
reference
Yeah.
for where is the statistical noise floor, whether it's
Okay.
the light gray triangle or the dark gray triangle up in the northwest corner.
Okay, sorry about that.
Yeah.
Okay.
Yeah. Those aren't the speed up factors.
Okay, so the speed up factors were always some constant factor, not
Yeah.
difference in the power?
Yeah, so you can definitely see, I mean, it's really that last graph I showed you. I mean, that alone, you would say it's a prefactor. So I would say the dynamics and the character of the dynamics have not changed, but they are definitely faster.
Okay, thank you very much.
Yeah, yeah, and certainly this is, I mean, to me, sort of just finish off here. Besides all this right here, where I'm really headed with my own research within DWave is I'm really curious about these systems when you actually anneal way faster than what we're doing right now. So I'm particularly interested in increasing coherence, decreasing anneal time. Let's see if we can get those timescales comparable. If not, be annealing faster than our coherence time. I'm
Well, the
really
motivation-
interested we're going to see something there.
for my-
Dynamics ought
yeah.
to be different.
In Helmut's talk, I don't know if you remember, but there was the scaling of the LHZ, Chimera, and Classical.
Yep.
And I pointed out that the Chimera, the embedding for the Chimera, there's good ways to do it, bad ways to do it, better ways to do it. And you've shown that right here, that you have 500 times faster when you do good embedding versus bad embedding. Some people would say maybe my embeddings are even better than D-Wave's embeddings, and then even my embeddings are not the best. You can get way better than that, right? So, I mean...
So the details of the embedding definitely matter, and it requires some knowledge of the physics of these phase transitions. At least being aware
But
of
that's
where they
not to
happen.
say anything bad about Helmut's work. I'm very, very...
But to play my own devil's advocate,
Yeah.
I mean, this last graph I showed you here, as I said, is prefactor alone. And if I wanted to really be the devil's advocate, say, well, that's just a prefactor. I'll wait till Intel gives me a next generation processor, and I'll beat that. This last statement I made about increasing coherence, reducing anneal times, I mean, get into a dynamically different regime. At that point, all bets are off. Quantum Monte Carlo, not going to work in coherent regime. It's not a fair comparison.
Okay, I'll just say I'm a very big fan of his work. I just it is a point I wanted to make that good embeddings can improve things. It's hard to compare when you're not saying what specific embedding you're using, or you're saying the specific embedding you're using, but that might not be the best. So it is hard to compare.
Yep, fair enough.
Thanks.